Dear friends, Maths Aspirants is a community of mathematics students, research scholars, and teachers from various parts of India. And we used to arrange several online problem solving sessions to help the students who prepare for different competitive examinations like IIT JAM, CSIR NET, GATE, NBHM, etc. As a part of that series, today we have a session on the theory of matrices, and we have Miss Annu is with us. She's a research scholar in Maharshi Dayanand University, Rohtak, Haryana. Miss Annu qualified IIT JAM examination in 2019 with All India rank 101, and she has done her B.Sc from Hindu College, Delhi University, and she did her M.Sc from IIT Kanpur and now pursuing PhD at MDU, Rohtak, Haryana. I hereby express my sincere gratitude to her for joining with us. And I hope that today's session will be a really good one because there will be lots of problems from the area of matrices. So she will discuss from the very beginning of matrix theory. And I'm sure that this session will be really helpful to all of you. I welcome everyone to this program. Welcome, Annu.
And I welcome you all in today's session. So we will be discussing, we will be starting from basics of matrices and will then gradually continue to some properties of matrices, then inverse, determinant, and rank. And if time permits, we will cover the basic of a system of linear equations. So matrix is an arrangement of mn elements in a rectangular array of m rows and n columns. Next, we have a row matrix, a matrix with one row and any number of columns, that is called a row matrix. And in similar terms, a column matrix is a matrix which has one column and any number of rows. Next, we have a null matrix. A null matrix is a matrix in which all the entries are equal to 0, and it is not necessarily a square matrix. It can be any matrix, any rectangular form of a matrix. So what is a square matrix? A matrix which has equal number of rows and columns, that we term as a square matrix. Next comes the diagonal matrix. A matrix in which the entries which are on the diagonal. For example, here this is called the principal. Sorry, the entries where 1, 2, 3 are present. That is called the principal diagonal of a matrix. And a matrix which has entries only on the principal diagonal and all other entries are 0, that is termed as a diagonal matrix. For a scalar matrix, that one more thing, diagonal matrix is always a square matrix because only then we can construct a diagonal within a matrix. Next, we have a scalar matrix. Scalar matrix is basically a diagonal matrix, but the entries on the diagonal, they are all equal to some scalar. They cannot be different. For like in this matrix, the entries were 1, 2, 3, 4. We can have any distinct number of distinct numbers there. While in scalar matrix, all the entries will be equal. Next, we have identity matrix, which is again a diagonal and a scalar matrix where the non-zero entries, that is the entries on the diagonal, are equal to 1. Next is an upper triangular matrix. So matrix, like we can draw a matrix in this. Here is an example of a upper triangular matrix where like the entries which are below the principal diagonal, they are all equal to 0. That is the entries where the I, which we normally term as the number of row, and j, which is the number of the column. So for I greater than j, if aij is equal to 0, in that case that matrix is called upper triangular. And lower triangular matrix is the matrix in which the entries above the principal diagonal, they are 0. So in upper triangular, the entries which were below the principal diagonal, they were 0. And in lower triangular, the entries above the principal diagonal, they are equal to 0. Next is when do we say that two matrices are equal? So if they have the same type, means their order is same. If they are both like a square matrices, if one is a square, then other has to be square. That is, they are of the same type, and the corresponding entries of the matrices are equal. So, that is, if the first position, we term the first position of the matrix as Aij, then Aij for both should be equal. For example, here we have 1, 1 and 4. So in the other matrix, we have we should have the same value at exact same position. Next is multiplication of two matrices. Now we are considering some operations of matrices. First one, if we consider, that is sum of matrices, which is equal to component wise sum. Similarly, the subtraction. For multiplication of matrices to exist, the number of columns of first matrix should be equal to the number of rows in the second matrix. These are some of properties of multiplication of matrices. The most important property is that it is this matrix multiplication is not always commutative. That is, AB must not be equal to, that may not be equal to B. Second, that matrix multiplication is associative, it is distributive. And we can have a case where like AB can be equal to 0, but BA may not be equal to 0 because they are not necessarily equal. Next is transpose of a matrix. So if we interchange the columns, if we interchange the matrix, like the rows of the first row of matrix is converted into the first column, second row of matrix is converted into second column. So in this way, if we interchange rows and columns of a matrix, we get the transpose of a matrix. And if the order of that initial matrix was m cross n, then the order of transpose of a matrix will be n cross m. These are some properties of transpose of a matrix. That is, if we add two matrices and then they take their transpose, it will be equal to sum of the individual transposes of each matrix. If we multiply a matrix by a scalar and then take the transpose, we can take the scalar completely out of the matrix and then take transpose of that matrix only. Transpose of a matrix is equal to the matrix itself. And this fourth property is very important, that when you apply transpose to the product of two matrices, then it follows reversal law. That is, if we are taking transpose of AB, then it will be equal to B transpose into A transpose and not A transpose into B transpose. That case, that AB whole transpose is equal to A transpose B transpose will only be possible if AB is equal to BA. Next, we have symmetric matrices. A square matrix is called symmetric if the transpose of matrix is equal to itself. Some properties of symmetric matrices are that in case of symmetric matrices, all the elements are real and elements above and below the diagonal elements. If we consider the space to be like real space, or if even in complex space, the matrices, the entries on the diagonal of the matrix, like here we have ABC. These ABC, they have to be always real. Next, the diagonal matrix, scalar matrix, and unit matrix. These are all symmetric matrices because in these matrices we have entries only on the diagonal and all other entries are 0. So the transpose of matrix is always equal to the same matrix. Next, if A is a symmetric matrix, then any scalar multiple of that matrix is also symmetric. If we have A and B as two symmetric matrices of same order, we considered same order here because we are taking addition and subtraction of matrices, and that is possible only if they have the same order. And we are multiplying both these matrices by some scalars. So if we take we can say a linear combination of symmetric matrices, then that linear combination will also be a symmetric matrix. This was the property that if A and B are two symmetric matrices of same order, then AB is symmetric if AB is equal to BA. Because if we take the transpose, it will follow the reversal law. So we will get AB transpose is equal to B transpose A transpose. And where B and A, if they both are symmetric, so B transpose can be replaced by B, A transpose by A, and hence we get AB that is equal to BA, which should be equal to AB to make it symmetric. Next, we have that AB any square matrix, then A transpose and A transpose A, they both are symmetric. If A is a square matrix, then A plus A transpose is also symmetric matrix. If A and B are two symmetric matrices of same order, then AB plus BA, that is also a symmetric matrix. And any power of a symmetric matrix, that is always a symmetric matrix. The other matrix we have is skew symmetric matrix, in which the transpose of a matrix is equal to the negative of the same matrix. In symmetric matrix, we had that A transpose is equal to A. In skew symmetric, we must have A transpose is equal to minus A. This is a very good property of skew symmetric matrices, that all the entries of the on the diagonal of a skew symmetric matrix, they are equal to 0, because for that entry should be equal to its negative, because the transpose doesn't change the position of diagonal entries. So Aij should be equal to negative of Aij, and this concludes that every entry on the diagonal that is equal to 0. In the case of skew-symmetric matrix, the elements above and below the principal diagonal are of opposite sign. You can think of this as a mirror placed on the diagonal. In case of symmetric matrices, uh, along this diagonal, they should have the same value, but in skew-symmetric, there should be a change in sign. If A is a square matrix, then A minus A transpose, that is skew-symmetric. And this is similar to the earlier case, that the linear combination will always be skew symmetric if the matrices A and B are skew symmetric. If A and B are skew symmetric matrices of same order, then AB is also skew symmetric if AB is equal to minus BA. Remember, in the case of symmetric matrices, it was AB is equal to BA. Again, if A and B are symmetric matrices of same order, then AB minus BA, this must be skew symmetric. And if A be any skew symmetric matrix, then all positive odd integral powers will be skew symmetric. We are not considering even powers here. In the case of symmetric matrices, any power of that matrix was a symmetric matrix. But in case of skew symmetric, we are considering only odd integral powers of A. Next, every skew-symmetric matrix of odd order, that is singular, we use this result in a very large number of questions. One more thing, if the order of the skew-symmetric matrix is even, in that case, its determinant is a perfect square. And every square matrix that can be uniquely defined as sum of symmetric and skew-symmetric matrix. So if in any question it is asked that you are given a matrix A, and if it is said that what will be the symmetric part of that matrix, then it is equal to 1 by 2 of A plus A transpose, and the skew-symmetric part of that matrix is 1 by 2 A minus A transpose. You can easily verify that this half of A plus A transpose is symmetric, and half of A minus A transpose is skew symmetric. Next, we come to orthogonal matrices. The matrices for which A transpose is equal to identity, which is equal to A transpose A. These are called orthogonal matrices. Some basic properties are, because, okay, so when we define inverse of a matrix, we say that a matrix B is inverse of A if AB is equal to BA is equal to identity. So in this case, because A transpose is equal to identity and A transpose A is equal to identity, we can say that A transpose is actually inverse of A. If A is orthogonal matrix, then determinant of A is equal to plus minus 1. This property of orthogonal matrix is widely used in the topics of eigenvalues and eigenvectors. That if A is orthogonal, its determinant will be equal to plus minus 1. That is, the modulus of it is equal to 1. If A is orthogonal, then A transpose is also orthogonal. If A is orthogonal, then its inverse is also orthogonal matrix. If A and B are two orthogonal matrices, then AB is also orthogonal matrix. Next, we have the conjugate of a matrix. In case of complex numbers, what we do is for any number A plus iota B, its conjugate is equal to A minus iota B. That is, we change the sign of iota. Similarly, while taking conjugate of a matrix, we take conjugate of each of the entry of a matrix. For example, here we had 1 plus iota. So if we are taking conjugate of A, we will change the sign of iota here. We will get 1 minus iota. This is a real number. It won't be affected. So 1 minus iota, 2, 3. This will change to 2 plus iota. And we can take conjugate of any rectangular matrix. It need not be any scalar square matrix. These are some properties of conjugate of a matrix. A plus B conjugate is equal to A conjugate plus B conjugate. In this multiple, like if we multiply a scalar k by a matrix and then take the conjugate, it will be equal to, you can take the scalar out, take its conjugate, and then multiply with conjugate of the matrix. This is similar to the case of complex numbers, that if you take double conjugate, it gives you the same number here, the same matrix. And the conjugate is, it does not follow any reversal law. It is just AB conjugate is equal to A conjugate into B conjugate. Next term is transjugate of a matrix, which is formed of two words, that is transpose and conjugate. So we will take transpose of the matrix and the conjugate. You can either take first transpose and then form the conjugate, or first you can take the conjugate and then do the transpose. They both will give you the same result. These are the properties. A plus B tranjugate is equal to A tranjugate plus B tranjugate. If you are taking tranjugate of a scalar multiplied with matrix, take the uh, conjugate of the scalar and multiply it with the tranjugate, because you cannot take transpose if you are taking the scalar out. Here is the important property, that tranjugate follows reversal law, because when you are taking tranjugate, you are basically first, or at any step you are doing transpose, and the other thing you are doing is taking conjugate. Conjugate doesn't follow reversal law, but we had seen that transpose of a matrix follows reversal law. So tranjugate in a whole, it will follow the reversal law. In similar terms of symmetric and skew symmetric, we have Hermitian and skew Hermitian matrix. Here, if A tranjugate is equal to A, then the matrix is called Hermitian. These are the properties, that in case of Hermitian matrix, all the diagonal elements are real. This happens because the diagonal entries, they do not change while taking the transpose. So a number should be equal to its conjugate, which is possible only if its imaginary part is equal to 0. Next, if A is any Hermitian matrix, then Ka is also Hermitian, where K is any real number. Notice we have said that K is any real number here, and not like complex. This does not hold for complex numbers. If A and B are two Hermitian matrices of same order, then their linear combination is also Hermitian for some real λ1 and λ2. Again, we are taking real numbers here. If A and B are two Hermitian matrices of same order, then AB will be Hermitian if AB is equal to BA. If A is any square matrix, then A conjugate and A conjugate A, these both are Hermitian. A be any Hermitian matrix, then all positive integral powers of A, those will be Hermitian matrices. In case of symmetric and skew symmetric, we saw the symmetric part and skew symmetric part. Similarly, we have Hermitian part and skew Hermitian. But here we have that every square matrix can be uniquely written in the form of P plus iota Q. In this form, where both P and Q, they are Hermitian matrices. In this case, the value of P will be equal to 1 by 2 of A plus A conjugate, and the value of Q will be equal to 1 by 2 iota 1 minus A conjugate. Now, skew Hermitian matrices are the matrices where A conjugate that is equal to minus of A. Properties, very important property that in case of skew Hermitian matrices, all the diagonal elements, they are either zero or they are purely imaginary. They cannot, the skew Hermitian matrix cannot have a non-zero real number on its diagonal. If A is any skew Hermitian matrix, then Ka is also skew Hermitian. Again, the linear combination is skew Hermitian. If A and B are Hermitian matrices of same order, then AB minus BA is also skew Hermitian. And AB will be skew Hermitian if AB is equal to minus BA. And if A is any square matrix, then A minus A conjugate is skew Hermitian. These are some of the properties that can be used directly. That if A is Hermitian, then iota A that will be skew Hermitian. If A is skew Hermitian, then iota A will be Hermitian. Next we have if B conjugate AB is Hermitian or skew Hermitian, it will depend whether the middle term here, that is the A matrix, this is Hermitian or skew Hermitian. It will depend on this one. This for similarly for symmetric and skew symmetric matrices. Next we have unitary matrices, which are similar to like in the earlier case where we saw orthogonal matrices where we were taking A transpose is equal to identity. Here we are taking A conjugate is equal to identity is equal to A conjugate A. These are the properties that its inverse is equal to its conjugate. Its determinant is modulus of its determinant is equal to plus minus 1. If A is unitary, then A conjugate is unitary. If A is unitary, then A inverse is also unitary matrix. If A and B are two unitary matrices, then AB is also unitary matrix. Next, we have a periodic matrix, a matrix for which A power k plus 1 is equal to A, where k is the least positive integer for which this equation holds. That is called a periodic matrix, and here k is called the period of the matrix. Next, idempotent matrices is a matrix where A square is equal to A. These are the properties. If A and B are two idempotent matrices of same order, then AB will be idempotent if and only if AB is equal to BA. If A and B are idempotent matrices, then their sum will be idempotent if and only if AB is equal to BA is equal to 0. And if A is an idempotent matrix and A plus B is equal to identity, then A is idempotent and AB is equal to BA, that will be equal to 0. Next, we have involutory matrices where the square of the matrix is equal to the identity matrix. From this A square is equal to I, we can clearly see that identity is always involutory because I square is equal to I. And any matrix will be involutory if I plus A into I minus A, that is equal to 0. Next are nilpotent matrices, the matrices for which the some power of the matrix is equal to 0, but here we are considering that A power m is equal to 0, but A power m minus 1 is not equal to 0. So null matrices do not fall in this category. Next, we have determinants, minors, and adjoint of matrices. Determinant is taken, it can be taken along any row or any column of a matrix. Like for this 2 cross 2 matrix, determinant of the matrix is equal to A11, A22 minus A21, A12. In this 3 cross 3 matrix, you can expand it along your first row, second row, third row, along any row you can expand it. If we are multiplying, like if we are taking A11, then we are multiplying it with the minor, corresponding minor, which is A22, A23, A32, A33. In this way, we determine the determinant of a matrix. Its properties are determinant of A is equal to determinants of its transpose. If all the entries in a matrix, we have a matrix here, and if all the entries in any row, they are equal to 0, then the determinant of the matrix is always equal to 0. Or if all the entries in any column are equal to 0, then its determinant will be equal to 0. And if any two rows or columns of matrix are identical, in that case also the determinant is equal to 0. We have three main properties of determinants, like if we can interchange the rows and columns. If we are considering like determinant of a matrix A, this is equal to, we are taking determinant. Then if we interchange the first row with second row, like we are shifting first row to the second place and the second to the first, then there will be a negative sign in the determinant. And we can always multiply if the first row, like it has a scalar k in common. Here we have like k as a common factor in the row. Then we can take k common, and then we can write the matrix here. If the scalar is common in the complete matrix, like in first row we can take k common, in second row also it is common, in third row also, then it will be equal to k to the power, that is the order of the matrix. And if A is a triangular matrix, then determinant is equal to the product of diagonal elements. This is the property that we were just discussing. The determinant of Ka is equal to k power n into determinant of A. And adding a scalar multiple of any row to another row doesn't change the value of the determinant. A matrix whose determinant is equal to 0 is called a singular matrix. And the case when this is not equal to 0, it is termed as non-singular matrix. Now, for A is equal to Aij be any square matrix, then the notation Mij. This denotes submatrix of A with order n-1 cross n-1, obtained by deleting its ith row and jth column. And this determinant of Mij, that is called the minor of the element Aij of A. For cofactor, we multiply the minor with -1 raised to the power I plus j. Next, we have adjoint of a matrix, which is used in determining the inverse of matrix. So the transpose of matrix of cofactors of elements is denoted by adjoint of A, and it is called the adjoint of matrix A. This is the property that A into its adjoint is equal to adjoint of that matrix into A, which is equal to modulus of A, determinant of A. If A is any non-singular matrix of order n, then determinant of adjoint A is equal to determinant of A raised to the power n-1. Next, we have some elementary transformations for a matrix. So we can, while like solving linear equations or finding the rank of a matrix, we require these elementary operations. The first one is we can interchange any two rows and columns of a matrix. Like first and second, we can always interchange them. Second thing is we can multiply any row, like first row, second row, by any scalar. Third thing is we can multiply a row by a scalar and we can add it to any other row without changing its type. When these operations are applied within a row, these are called elementary row operations. And if they are applied within columns, they are called elementary column operators, but we use elementary row operations more widely. Next, we have equivalent matrices. So a matrix B is said to be equivalent to A if it can be obtained from A by finitely many successive elementary transformations. That is, if by using these three operations, again, the adjoint of a matrix that follows the reversal law, that is adjoint of AB is equal to adjoint of B into adjoint of A. If for any square matrix A, adjoint of A, if we consider the matrix adjoint A, then take its transpose, it will be equal to first take the transpose of the matrix and then compute the adjoint. And adjoint of a symmetric matrix is always a symmetric matrix. This is the inverse of a matrix that we defined earlier, that a matrix B is said to be inverse of a matrix A, or we can reverse their roles if AB is equal to BA is equal to identity. And the necessary and sufficient condition for a square matrix A to have inverse is that it should be non-singular. Determinant of A should not be equal to 0. Now, inverse of a matrix, it again follows reversal law. That is, AB inverse is equal to B inverse A inverse, which was the case in transpose as well as in adjoint. If we are taking inverse of a finite number of matrices, then it again follows the reversal law. A transpose inverse is equal to A inverse transpose. And if K is a non-zero number, we are multiplying that number with the matrix, then take the inverse, it will be equal to multiply the reciprocal of that number with inverse of the matrix. Okay. Next we have rank of a matrix. The standard definition of a rank is a positive integer R is said to be rank of a non-zero matrix A if there exists at least one minor in A of order R which is not equal to 0, and every minor of order greater than R that must be equal to 0. In that case, R is called the rank of a matrix. But while doing questions, what we do is the rank, how we compute the rank of a matrix. Like we are given any matrix here, if this is the given matrix, we will apply elementary row operations, the three operations that we studied earlier, and convert it into reduced echelon form and check the number of non-zero rows in that form. The number of non-zero rows gives us the rank of the matrix. Here we are given this matrix A, and we are asked to find the rank of the matrix. So by the definition, we can compute, because determinant of A is equal to 0, so it cannot have rank equal to 3. So next we compute the minors, that is B1, corresponding to this entry. So we have 2, 3, 5, 7, that is minus 1, which is not equal to 0. Hence the rank of this matrix is equal to 2, because we found a minor whose determinant is not equal to 0, but determinant of any higher order that is equal to 0. So let us just go to some questions like this. We are given 3 points, x1, y1, x2, y2, x3, y3, and we are asked that these points are collinear if the rank is. So we know that for any 3 points, the area of the triangle is given by x1, y1, 1 half of this determinant. And if 3 points are collinear, then it means the area will be equal to 0. So the area here is equal to 0. So the rank of the matrix cannot be equal to 3, because we just saw by the standard definition that for that this, if this is not equal to 0, we could have said that rank of A is equal to 3, but in this case, because the points are collinear, so the rank cannot be equal to 3, hence it will be less than 3. Next, we have this question, that under what condition the rank of this matrix is equal to 3. So for the rank of the matrix to be equal to 3, we should have the determinant is not equal to 0, because if this determinant is equal to 0, in that case the rank will always be less than 3. So compute the determinant of the matrix, that is 2, taking 2 out, 1 into x minus 0 into 2 minus 4 multiplied by 2 into x minus 1 into 2 plus 2 multiplied by 2 into 0 minus 1. Then this should not be equal to 0. So in the case when x is not equal to 1, in all those cases the rank of this matrix will be 3. Uh, this is normal method to determine rank. This is not used to determine a rank, but to determine what will be the form of the matrix. Like if we are given any 4 cross 4 matrix and we are asked to find the normal form of this matrix. So what we will do is we will use the elementary row operations to reduce it in the row reduced echelon form. And if we get a matrix of this type, that is identity, we get an identity here and all other entries beside this are 0, then this is the form of that matrix. Again, if the last row becomes 0, this is the required form. If the last column becomes 0, this is the form. And if there is no like row or column which is 0, then we say that it is of this form. Let us now compute the rank of a matrix by row operations. Sorry, column operations. We can use row operations as well as column operations, any operations we can use. So here we have the matrix 1, 2, 3, 2, 5, 7, 3, 8, 9. First we are taking C2, R2 changes to R2 minus 2 R1. So that will be 2 minus this. Okay, let us first see what is the standard way to reduce a matrix into row reduced echelon form. So what we do is we will first check if this entry is 0 or non-zero. If it is non-zero, then it is fine. If it is 0, change this row with any other row whose first entry is non-zero. You can change it with any other row. And in that case, first make this entry to be non-zero if it is possible to do so. Else move to the next entry. If all the entries here are 0, then you will have to move to the next entry and make this non-zero. This is the first step. Once you have made the first entry to be non-zero, convert the entries below that entry into 0 by multiplying by respective scalars. For example, here we had 2. So what we will do, we will multiply row 1 by 2 and will subtract it from second row. So when we multiply this by 2, we get the entries 2, 4, and 6. And then we subtract this from row 2, so we get 0, 1, and 2. Similarly, for third row, to make this entry 0, we have to multiply first row by 3 and then subtract it from here. So this is the matrix that we will get. Next we will do is, here we have applied the column operations, like C2 changes to C2 minus 2 C1, C3 changes to C3 minus 3 C1. You can apply these or you can continue applying the row operations here. For example, when you got this, what we can do is we can change this matrix to like R3 can be changed to R3 minus R2. In that case, this entry will become 0 and here we will have minus 2. So we will have non-zero entries here, here, and here. So that will be the reduced echelon form in which rows in a matrix. So the rank of a matrix will be equal to 3. This is a very standard example where you can remember the result of this, that for this type of matrix where we are taking squares, 1 square, 2 square, 3 square, 4 square, the rank of this matrix is equal to 3. It can be computed in a similar pattern. This is the note we were discussing that while computing the rank of a matrix, you need not find the minors every time because that is a very tedious task. So what you can do is you can find the number of non-zero rows by using elementary row transformations. That is the number of pivot elements in that case. So if we have this matrix one, if you are asked to find a rank of this matrix 1, 2, 3, 2, 5, 8, 3, 7, 9. So what we will first check if this entry is non-zero or not. This is non-zero. We can move to the second step to convert this entry to 0 and this entry to 0, similar to the above. Next, we have a rectangular matrix in which we are asked to find the rank of the matrix. Again, this is non-zero. Multiply first row by 2 and subtract it from this. Multiply first row by 3 and subtract it from third row. These are the two row operations that we applied. This will result into this matrix. Next, if we have this entry non-zero and we have converted all the entries below this to be 0, we will move to the next row and try to convert this entry in non-zero terms. Check if this is non-zero and all the entries below this will be converted to 0. So the same we have done here, that R3 is changed to R3 minus 2 times of R2. We get this one. Now this is a echelon form, and these are the only non-zero rows we have, row 1 and row 2. So the rank of the matrix will be equal to 2. These are some questions. That if A and B are 3 cross 3 real matrices such that rank of AB that is equal to 1, then what will be the then rank of BA cannot be, it is asked if 0, 1, 2 or 3. So if A is a 3 cross 3 matrix, B is a 3 cross 3 matrix, then AB will be a 3 cross 3 matrix. That is fine. Now a rank of AB that is given to be 1. If the rank of a 3 cross 3 matrix is equal to 1, it means that its determinant is equal to 0. Because only in that case the rank can be equal to 1, that is all the minors which are higher than this, like all 2 cross 2 minors of 3 cross 3, they are equal to 0. Hence the determinant of the matrix AB that is equal to 0. If determinant of AB is 0, this means determinant of A is 0 or determinant of B is 0. And this gives us that determinant of BA will be 0, and hence rank of BA cannot be equal to 3. Because if it is equal to 3, then the determinant should have been a non-zero number. So the correct option is option D. Next, we are asked to find the rank of this matrix. So we have 148,
Ma'am, I
210,
have
22, 0, 4, 12. First entry is non-zero. There is no need to change it. This is already 0. So what we will do is we will convert this to 0 by multiplying R1 to 2. That is 2R1. We will compute R2 minus 2R1. So we will multiply this by 2. We will get 2, 8, 16. And then subtract this from R2. So we will get 0. 10 minus 8 is 2. 22 minus 16 is 6. Again, we have to check if this is non-zero or not. Since this is non-zero, we will convert this to 0 by multiplying R2 by 2, that is 2R2, and we will subtract this from R3. That is, the next step we do is R3 changes to R3 minus 2R2. This is the matrix. Next, what we can do is R3 changes to R3 minus R2 because these both are same. So we will get there 0, 0 and 0. So the rank of the matrix will be equal to, because only these two rows are non-zero, so the rank will be equal to 2. The next question is the number of, we are asked that what is the number of, how many 2 cross 2 matrices over Z3. Z3 is a group which has entries 0, 1 and 2 over addition. So we are asked what are the number of matrices over Z3 whose determinant is equal to 1. So this is a standard formula that you can remember. That order of this is SL and ZP. SL means spatial linear. These are the matrices whose determinant is always equal to 1. Those matrices are called spatial linear matrices. This is the order of matrix. This is this order of the group. So this is the formula that p power n minus p power 0 into p power n minus this. This is a very useful formula. You will have to remember this. So in this case, n is equal to, like the order of the matrix is 2. So n is equal to 2 and p is equal to 3. Put the values, the answer will be 24. This is the case. We use this because here we were given that how many matrices exist for which determinant is equal to 1. And SL, that is spatial linear matrices, are the matrices whose determinant is 1. This is a general result that for uh, any general linear matrices, the order is equal to this. This is not used in this question, but it is like for, we considered the case for spatial linear. So for general linear matrices, this is the formula. Next we have, we are given a matrix M which is equal to cos alpha, sin alpha, iota sin alpha, iota cos alpha. And it is given that this is a unitary matrix. We have to compute the value of alpha, the angle here. So because this is unitary matrix, so we have M into M of M conjugate, that is equal to M conjugate into M, and this is equal to identity. So M conjugate here will be, first you can take the modulus. In that case, we have here cos alpha, sin alpha, minus iota sin alpha, and minus iota cos alpha. And then we have to take the transpose. So the matrix that we get is cos alpha and sin alpha is first column, and minus iota sin alpha minus iota cos alpha, that is this is the second column. So this is the conjugate of the matrix. Now we have M conjugate is equal to identity. So when we compute the product of these two matrices, the first term we get is cos theta plus, that is cos alpha into cos alpha plus sin alpha into sin alpha, that is cos square alpha plus sin square alpha, which is equal to 1. So this entry is 1. Next we have cos alpha into minus iota sin alpha plus sin alpha into minus iota cos alpha. So what we will get is minus 2 iota sin alpha cos alpha. This term is this. And this is again iota sin alpha into cos alpha plus iota cos alpha into sin alpha. Sorry, this will be plus, so it is 2 iota cos alpha sin alpha. And the last term will be minus iota square sin square alpha, which is equal to minus of minus 1 of sin alpha, sin square alpha, and minus iota square cos square alpha. This is again 1. So the matrix that we got is 1 minus 2 iota sin alpha cos alpha, 2 iota sin alpha cos alpha, and 1. And this is equal to your identity matrix because this is a unitary matrix. So these two entries are fine. We have to compute the value of alpha from these terms, that 2 iota sin alpha cos alpha, that is equal to 0. This implies iota into sin 2 alpha is equal to 0. We can compute the value of alpha from here. This term implies, because iota is not equal to 0, so sine of 2 alpha, that is 0. Hence 2 alpha is equal to a multiple of pi, where n belong to her integer. So alpha is equal to n pi by 2, n belongs to z. So this holds for all integers. But if we see the options, like we are given, these are the odd integers. This term reduces to n plus pi by 2. This is the same result that we can write it in that form. So the correct option for this is option A. Next we have, if A and B are n cross n matrices such that rank of A and rank of B, it is equal to n, we have to find rank of a matrix C which is equal to A cube B square A. Now because rank of A is n, rank of B is n, so determinant of A and determinant of B, they are not equal to 0, because if they were equal to 0, then the rank of these matrices should have been less than n. Hence this determinant is not equal to 0, so determinant of C, which will be equal to determinant of A cube, determinant of B square into determinant of A. Because this is no, these terms are non-zero, so determinant of C is not equal to 0, and hence by definition the rank of C will be equal to n. Remember that rank of A plus B is not equal to rank of A plus rank of B, and rank of AB is not equal to rank of A into rank of B. Rank of AB is always less than equal to rank of A, minimum of rank of A and rank of B. Okay, so this is that we have a matrix A is equal to Aij, where Aij is minimum of I comma j, Ij varying from 1 to n. We have to find the rank of the matrix. So we have a matrix. Let us first see this case for a 3 cross 3 matrix. We are considering n equal to 3 here. So in that case, what we are told, that the value of every entry is equal to minimum of Aij. So the first entry is A11. Minimum here will be 1 only. So the first term will be 1. The second term that appears here is A12. Minimum of 1 and 2 is 1. So this will again be equal to 1. This will be 1. For this entry, we have A21. So minimum is equal to 1. Here we will get 2, 2, 1, 2, 3. This will be the matrix that we will get. Okay. We have to compute the rank of the matrix. So what we will do is, because this entry is non-zero, so the first row remains same. We use this sign while computing this similar sign. So the row second changes to, like we change R2 changes to R2 minus R1. So this will be 0. 2 minus 1 is 1. 2 minus 1 is again equal to 1. And R3 is changed to R3 minus R1. So here we will get 0, 1, and 2. Now this is non-zero. All entries below this are 0. We will move to the next row. Here we have this entry to be 0. Next step is to make this 0. So what we will do now is compute R3 changes to R3 minus R2. So this is equal to 1, 1, 1, 0, 1, 1, 0, 0, 1. So we get 3 non-zero entries. So we have 3 non-zero rows. So the case when we considered n equal to 3, the rank came out to be 3. So there is a chance that the result may be that the rank of matrix is equal to n. We can compute this for like any general matrix considering this order to be equal to n. In that case, what we will get is this matrix will expand. Like here we will get all entries to be equal to 1. All other entries here will be 2. Here will be 3. We will get 1, 2, 3, 4. Other entries will be 4. And in similar term, this will progress. So, what for a general case, what we will do is that again R2 will change to R2 minus R1. Each row we will subtract R1 from each row. Then we will subtract the case that we did here. That will move in the similar pattern, and we will get a lower an upper triangular matrix, like we got in the case of 3 cross 3 matrices. And we can conclude that rank of this matrix A is actually equal to n. Okay, let us now move to system of linear equations. Just a minute. Okay, if M is a matrix, this is the given matrix, and we are asked to compute the rank of M. So this is again the same thing. We consider the matrix. This is a rectangular matrix converting into row reduced echelon form. What we will do is add first row and second row. Then this computation R3 changes to R3 minus 2R1 and R4 changes to R4 plus R1. Continuing in the same way, we will get only two non-zero entries, and hence the rank of this matrix will be equal to 2. If a matrix is given A, that is 2, 1, 3, minus 1, I is the identity matrix, and we are asked that which of the following is a zero matrix. So one way is you can directly put the values of like A square. You can compute A square, A, and 5i. But because you are asked that which of following is a zero matrix, so this can be done by using the characteristic equation, which is considered, which is a topic in eigenvalues and eigenvectors. Now, if we are given two matrices P and Q such that P is Hermitian, Q is Q Hermitian, and we are asked that which of
Ma'am,
the following, yes,
can you please explain the previous question once more?
okay. This one,
No, before this.
um, this one.
Yes.
Okay. So here we had a matrix M, that is 1, 1, 0, minus 1, 1, 2, 2, 2, 0, minus 1, 0, and 1. We were asked to find the rank of the matrix. So we will use the method of row reduced echelon form or row reduced echelon form. You can use whichever you want. So what we will do is, first thing is we will check this whether this entry is zero or non-zero. Because this is non-zero, we will convert all these three entries into zero. So for R2, what we will do is R2 will change to R2 plus R1. Because this is minus 1, so we will add R1 to this. R3 can be changed to R3 minus 2 times of R1. We will have to multiply this by 2, and to make it 0, we will have to multiply this by 2 and then subtract. Again, because this is minus 1, we will directly add row 1 in this. So what we will get is this minus 1 plus 1, this term will be 0. 1 plus 1, this will be 2. 2 plus 0, this will be equal to 2. For R3, what we did is we multiplied R1 by 2, so the entries were 2, 2, and 0, and subtracted this from R3. So 2 minus 2, 0, 0, and 0. For R4, what we did is we added R1 into R4. So we got 1 plus minus 1 is equal to 0. This will be equal to 1, and this is equal to 1. Now we have a non-zero entry here. All the entries below this are 0. So we will move to the next row, second row. We will check for this entry. This is non-zero, so we will convert all the entries below this to be 0. For easier computation, what we can do is, because both these entries are 2, we can divide R2 by 2 so that this converts to 1.
Yes, ma'am, understand. There is a calculation mistake in with me. Thank you, ma'am.
Okay, okay. So this was the question where we were given two matrices P and Q such that P is Hermitian, Q is Q Hermitian. So because P is Hermitian, so P is equal to P conjugate. Q is Q Hermitian, so Q is equal to minus of Q conjugate. We are asked which of the following will be a Hermitian matrix. The case, okay, so we will compute for individual part. For PQ conjugate, because this follows reversal law, we have to remember that. So PQ conjugate, that will be equal to Q conjugate into P conjugate. This is equal to, because Q conjugate is equal to Q. Sorry, Q is Q Hermitian. So Q conjugate is equal to minus Q and P conjugate is equal to P, which is not equal to PQ. And it is neither it is equal to PQ nor it is equal to minus PQ. So we cannot conclude that PQ will be a Hermitian matrix. For the second case, we are given iota PQ. So here, if we compute the conjugate, we will have to compute the conjugate because in the question we are asked if it will be Hermitian or not. Okay, so for computing the conjugate, because this is a scalar, we can take this out, and we had that property that if Ka conjugate, we are computing the conjugate, what we will do is we will take conjugate of A and we will compute conjugate of the matrix. So we are doing the same here. We are taking conjugate of iota and we have the conjugate of PQ, which is equal to iota conjugate is equal to minus iota and PQ conjugate is Q conjugate P conjugate, because Q is Q Hermitian, so this is minus Q and this is P, and this gives us iota QP. But this is not equal to iota PQ, therefore it is not a Hermitian matrix. For the next case, P plus iota Q conjugate. So this splits up for both terms. We had seen that A plus B conjugate is equal to A conjugate plus B conjugate. So we can split this conjugate. Again, this iota is a scalar. Take this one out with its conjugate. And this has its conjugate with this. So this will, because P is Hermitian, so P conjugate is equal to P. Iota conjugate is equal to minus iota. Q is Q Hermitian, so this turns to be minus Q. And this gives us P minus iota, and this minus will turn this into positive sign. So we will get P plus iota Q, which is equal to this matrix. So we got that P plus iota Q conjugate is equal to P plus iota Q. Hence, this matrix is a Hermitian matrix. Next, we had P minus iota Q. So P conjugate minus iota Q conjugate, moving in the similar pattern, we can see that this will give us P minus iota Q, and this will again be a Hermitian matrix. So option C and D, they both represent a Hermitian matrix here. We have another question, that product PQ of any two real symmetric matrices P and Q is. What we are given is, we are given symmetric matrices. So we are computing the product. If they are symmetric, so P transpose is equal to P, Q transpose is equal to Q. In the options, there are two things, that symmetric and antisymmetric. Antisymmetric is sometimes used for the terms Q symmetric. So we have to compute if this is, in these cases, it is symmetric or skew symmetric. So P transpose is equal to P, Q transpose is equal to Q because they both are symmetric. Now PQ transpose, this will follow the reversal law. So PQ transpose is Q transpose P transpose. Q was symmetric, so this we can replace this by Q. P was symmetric, so this is equal to P. So what we got is PQ transpose is equal to QP. To make this a symmetric matrix, if PQ is symmetric, PQ transpose should have been equal to PQ. But what we got is PQ transpose is equal to QP. So if we have PQ is equal to QP, in that case, we would have said that PQ is a symmetric matrix. So the correct, so what we were asked, the product PQ of any two real symmetric matrices P and Q is, first case is symmetric if for all P and Q, which does not hold true because PQ transpose came out to be QP. So this is not true. Second is never symmetric, which does not hold because we saw that if we have PQ is equal to QP, in that case, this matrix turns to be a symmetric matrix. So the option B is also not true. Third is symmetric if PQ is equal to QP. We have computed this, so this is the right option. Next is antisymmetric for all P and Q, which again does not hold because if a PQ was an antisymmetric matrix, then we would have got that PQ transpose is equal to minus of PQ. But QP is not equal to minus of QP, so option 4 is also incorrect. Okay. In the next question, we are asked about symmetric part of the matrix P, which is equal to product of a column vector and a row vector. So if we are asked symmetric part, we earlier saw that for any matrix A, the symmetric part is equal to 1 by 2 of A plus A transpose. So we will have to first compute the matrix P. This is of order 2 cross 1. This is of 1 cross 2. So P will be a matrix of order 2 cross 2, which we can see in the options also. So we will first compute P by multiplying these vectors. So P is AB into A minus 2B. This gives us this matrix A square minus 2A, AB, B into A minus 2 and B square. For the symmetric part, we have the result that symmetric part is equal to A minus A transpose. If we were asked to compute skew symmetric, we would have used this formula. Now what we will do is we will take the matrix P, we will take its conjugate, that is interchange the rows. Diagonal elements never change while considering the transpose of a matrix. So this AB will go at this place and B into A minus 2 will come here. So we will add these two matrices, that is component-wise addition, adding the corresponding terms only, and we have 1 by 2 here. We notice that here we have 2A into A minus 2. Here it will 2 into AB minus B. It will come out to be this. Here we will get 2 into AB minus B. And this is 2B square. We can cancel out, or we can take 2 common out of this matrix and cancel out this. So this is the result that we get. And check which option of these option is correct, which is D option. Okay. Let me see if there are any more questions. We will now move to system of linear equations. What is a system of linear equations? First thing, we will have a system, means we will have a number of equations. We will not be considering just one equation. We will have more than one equations. Then those equations will be linear. That is, we will have like x plus y plus z and not x square or y cube, like higher order terms we won't be considering. And these will be equalities, and none of them will be any inequality. So the first thing we consider is the non-homogeneous equations, the equations in which this part, that is not equal to 0. The equations for which the right hand side that is non-zero, these are called non-homogeneous equations. So for computing this, most of the questions of these are of the type that for what values you will be given in any like unknown term, k, alpha, or any other term, and you will be asked what is its value so that the system becomes consistent or it becomes inconsistent. If it is consistent, in what case will it have a unique solution? In what case will it have infinite solution? So this term that is written here, this is used for the notation of this is called augmented matrix. We will see this let us see this in this question. So we are asked to solve the following system of equations. In this, we can write this equation in the form. Here we will write the variables x, y, z, and this is equal to 6, 2, 1. So this, while multiplying, this term will get multiplied to the first term, this to the second term, and this to the third term. So the equation will turn out to be x plus y plus z is equal to 6, which is the first equation. So for writing the matrix representation, what we do is, here we will write the coefficients of the variable x, here for the coefficient of variable y, and here the coefficients of variable z will come. So we have 1, 1, 1, 1 minus 1, 1, 2, 1 minus 1. So this matrix A, along with the entries on the right hand side, this matrix is called augmented matrix. Now the rank of the matrices is used to decide whether the system will be consistent. Consistent means whether it will have a solution or not. Consistent is if the system has a solution, it is called consistent. If it does not have a solution, it is called inconsistent. Again, if it has one solution, it is said to have unique solution, and more than one, it turns out to be an infinite. It will either have a unique solution or will have infinite solution. These are the two possibilities in consistent system. So what we will do is we will find the rank of this matrix, rank of A with B, that is augmented matrix, and compute it, compare it with the rank of matrix A. If these are equal and this is equal to, first thing is if these are equal, then we will have a solution for sure. Either it will be a unique solution or it will be an infinite solution. But whenever this equality holds, we will get a solution. If this equality doesn't hold, the system will be inconsistent. Now when this equality holds, if it is equal to the number of variables, like here we had x, y, z as 3 variables. So if we compute here rank of augmented matrix A, B, and then A, and if this turns out to be 3, in that case, the system will have a unique solution. But if it turns out to be less than 3, then it will have an infinite solution. So the augmented matrix will be this 1, 1, 1, 1 minus 1, 1, 2, 1 minus 1. This will be the right hand side. Again, applying the row operations, we will change this to R2 changes to R2 minus R1. R3 will change to R3 minus 2 times of R1. The same operations keep on applying on this side also. We have to remember this, that all the terms here, they will change in the same pattern. All these operations will be applied on these also. So what we will get is this term. Again, R3 changes to R3 minus 1 by 2 R2. So the final matrix that we got is this. Here we have non-zero entry here, here, and here. So for this matrix, rank of the augmented matrix AB, that is equal to 3 because we have 3 non-zero rows in this. And rank of A matrix, that is if we do not consider this column, again this is equal to 3, which is equal to the number of variables 3 that we saw. X, Y, Z are 3 variables. So this system is consistent and it has a unique solution. To find the solution, you can do is like write first equation is again in the equation form x plus y plus z is equal to 6 minus 2y is equal to minus 4, and minus 3z is equal to minus 9. From these, you can easily compute value of y and z and put that value in first equation to get value of x. Again, we are asked to solve this system of equations. So we will form the augmented matrix, apply row operations. In this case, what we got is we have non-zero entries in only first and second row, but the third row is entirely zero. If we had any non-zero term here, in that case, rank of augmented matrix would not be equal to rank of A if this term was would have been like any positive term, if it were 1 or 2 or any of that type. In that case, the system would be inconsistent with no solution. But here, because this row is entirely zero and these ranks are equal, so it will have a solution. But because this is not equal to the number of variables, we had 3 as the number of variables, but this rank turns out to be 2. So these equations, this system, it has infinite number of solutions. For finding infinite number of solutions, again write this in the equation form, but we will get x plus 2y minus 3z is equal to 4, minus of y is equal to 0. We do not have any non-zero term for z here, so we will take z equal to, z is a free variable, we can take it to be any scalar. This is any scalar you can take. And here z is equal to k, y is equal to 0. You can compute the value of x, which is 4 plus 3 times of z, y is 0, and this is k. So x is equal to 4 plus 3k, y is 0, and z is equal to k. Whenever we place the value of k here, we will get a different answers. Because the solution is in the form of x, y, z, z can have infinite number of values because z can be taken as any k. So the system has infinite number of solutions. The only possibility was either we had a unique solution, as we saw in the earlier question. If it does not have a unique solution and is consistent, it will have infinite number of solutions. Another question where you are asked to solve the system. In this case here, this entry, it turned out to be non-zero. So rank of A augmented B, that is equal to 2, but rank of A augmented B, that is equal to 3, because we have non-entry, first row is non-zero, second row is non-zero, and third row is also non-zero. While if we consider only matrix A, that is matrix still here, the rank of matrix A, that is equal to 2. So these are unequal, so the system has no solution. This is the general type of question that is mostly asked, that find the value of lambda and mu in the system of equations this. For the case when it has a unique solution, an infinite solution, or no solution. Again, form the augmented matrix, reduce it into echelon form. We finally get to this step. So for a unique solution, what should we have? That rank of this augmented matrix should be equal to rank of A, which should be equal to the number of variables, which is 3. So lambda minus 3, this should not be equal to 0, because if this is equal to 0, then rank of A will be less than 3. So this should not be equal to 0. And if this is not 0, then mu minus 10, this should also be not equal to 0 for the case of unique solution. So we will get that for lambda not equal to 3 and mu not equal to 10, the solution will be unique. For infinite number of solutions, for if we are taking the case of infinite number of solutions, these two should be equal, but this should be less than 3. So because we have a non-zero term here, so it can we cannot reduce it to less than 2. So we will always have two non-zero rows. So we will say that for the case when rank is equal to 2. So to make the rank of these two matrices equal to 2, we will have to consider lambda equals to 3 and mu equals to 10. In that case, it will have infinite number of solutions. And for no solution, what we will have to do is, we will have to make this term 0 so that rank of A becomes 2 and this to be non-zero, so that rank of A augmented B, that is not equal to 0. So we will have lambda minus 3 is equal to 0 and mu minus 10 is not equal to 0. So the case when lambda is equal to 3 and mu is not equal to 10, that will give us the case of no solution. Again, for what values of lambda does the following system of equation have a solution? You can compute it in the similar pattern. Next is the homogeneous equation. Till now, we were considering the case of non-homogeneous equations in which this term, that is b, that was not equal to 0. In case of homogeneous, if b is equal to 0, we say that the system is homogeneous system. It has two possibilities. A homogeneous system will always have a solution because you can always take x to be equal to 0, that is a into that 0 vector, and it will always give you the answer 0. So homogeneous equations, they always have a solution. What we need to find in this is if the solution is unique or if it has infinite number of solutions. There is no case of inconsistency in case of in this homogeneous system. Now, if rank of the matrix A that is equal to the number of variables, then the system will be consistent with the unique solution. And if this is less than the number of variables, it will have infinite number of solutions. You can do this, or another simple method is, because we know that if determinant of a matrix is equal to 0, in that case the rank of the matrix that is less than the order of the matrix. So if determinant of A is 0, in that case it will be a singular, it will have non-trivial or infinite solutions. So trivial means the 0 solution. So non-trivial is it will have non-zero solutions, which covers the case of infinite solution. If determinant is not equal to 0, that is rank is equal to 3, rank is equal to the number of variables, hence that is that we will have trivial solution or a unique solution, and that solution is a 0 solution. Now we are asked to solve this system of equation. This is a homogeneous system. We can solve it like earlier by reduced echelon forms. Convert it into this. We saw that we see that we have only two pivot positions here. There is no pivot position corresponding to the second variable. We did not get any pivot position corresponding to second variable. So second variable, that is free. So we will take from here the equation will be x plus 2y plus 3z is equal to 0 and z is equal to 0. Y can be considered as any scalar k. From here we can compute x is equal to minus 3z minus 2y. This is 0. So the solution is x is equal to minus 2k, y is equal to k, and z is equal to 0. Again, we are asked to find the value of a variable lambda so that this has a non-trivial solution. So in this case, it is easier in case of homogeneous if we compute the values of this by using the determinant. We did not have this option in case of non-homogeneous equations, but for homogeneous equation, if they are asking that in what case will it have a non-trivial solution, so we will have to put the determinant equal to 0. Just put this determinant equal to 0, you will get the required value. Or you can use this that reduced form and compute the value from there. Let us see some questions. Now if 3x plus 2 plus z is 0, x plus 4y plus z is equal to 0, 2x plus y plus 4z is 0 be a system of equations, then you are asked that whether it is consistent or inconsistent. If it is consistent, it has a trivial solution because it will always have a solution that you can say because it is a homogeneous system. So option C is that it can be reduced to a single equation and so a solution does not exist. So C cannot be the right answer for this because it will always have a solution and it says that a solution does not exist. Now we have to compute whether it is inconsistent or it only has a trivial solution or not. So we have this matrix representation of this. We will get determinant of A. We will compute the determinant, and determinant turned out to be non-zero number. Because this is non-zero, the system will be consistent. It will have a unique solution, and that unique solution will be 0, 0, 0. That is the trivial solution. So the first option is incorrect. It was already, we need not compute anything to prove that this is incorrect, because a homogeneous system can never be inconsistent. It has only the trivial solution. This is the right answer. And the determinant, because this is trivial solution, we have computed that the determinant in that case should be non-zero. So this is also wrong. So option B is correct. Here we were asked to compute the rank of M that you can do by using reduced echelon forms. Next, we are given a system of linear equations. X plus y plus z is 3. Here we have an unknown k. So the value of k for which this system has infinite number of solutions. Because this is a non-homogeneous, so we cannot use the method of determinants. So we will use the row reduced form. Form the augmented matrix for this system. Now we will apply R2 changes to R2 minus R1, R1 changes to, sorry, R3 changes to R3 minus R1. We will get this. To make this one, for like easier computations, you can divide row second by 2, row 3 by 6, then reduce, subtract row, like compute R3 changes to R3 minus R2. So this 1 minus 1, that will be equal to 0. We will get a term, this term here only, and all other terms in this will be 0. So we were asked to find the value of k for which the system has infinite number of solutions. So to have infinite number of solutions, the rank of augmented matrix, this should be equal to rank of A, and this should be less than the number of variables, which is 3. Whatever value you choose, rank of A augmented B and will always be equal to rank of A, because this term is 0, so it is not going to affect that. So what we need to do is we have to make sure that 1 minus k upon 6 minus 1, this is equal to 0, because if this is not equal to 0, then the rank will be 3, and in that case we will get a unique solution. So computing this, we will get k is equal to minus 5. The first part, A option. Again, for any A belongs to R, consider the system of linear equations this. In unknowns x, y, and z, which of the following statement is true? You are given, you are asked if the given system has a unique solution for A is equal to 1, infinitely many solutions for A equals to 2, unique solution for A equals to minus 2, and infinitely many solutions for this. So use that elementary row operations here. This can be, there is an easier way you can do it, that like this also. Interchange row 1 and row 2 so that the first row has 1 over here. Or you can multiply the second row by A so that this becomes easier to solve. Compute this. This is the final matrix that we get. So we have to compute the values of A. The possible values of A that are given here are either for like A equals to 1, 2, and minus 2. For A is equal to 1, this is the value we get. So here we can see that the rank of A augmented B, that is equal to 3. We will interchange these two rows. So what we will have here is 1, 1, 0, 3, 0, 0, minus 1, minus 11, 0, 0, 0, minus 6. So rank of A augmented B is equal to 3, but rank of A matrix, that is only this matrix, that is equal to 2. So we will have no solution in this case. When A is equal to 2, again we will have a matrix of this form, which will give us no solution. And for A equals to minus 2, we can see that this is the required form. Here we will get the rank of A augmented B, that is equal to 3, which is equal to rank of A, which is equal to the number of variables, and hence we will get a unique solution. These are the most of the questions which are asked in these sections. If you have any doubt, you can ask.
Thank you, Annu, for this session on matrices, and you have covered almost all the important properties and basic results regarding the theory of matrices, especially from the syllabus of JAM examination. I'm sure that the session was really helpful to all the students who are seriously preparing for JAM examination. Now it is a time for interaction. Dear students, you can ask your questions, or you can share your comments regarding the class. Also, in the beginning, I have told you that Anu has a good academic record. She qualified JAM examination with a good All India rank, and she has got experiences from a premier institute like IIT Kanpur. And another interesting thing is that in the very first year of M.Sc itself, she qualified CSIR JRF with a All India rank 40. So you have lots of lessons to learn from her. So now it is your time to ask your queries. Yes, students.
Hello, ma'am. My name's Alina
Yes, hello.
Matthews. My name's Alina Anna Matthews. I'm a third year B.Sc student of Marthoma College, Tungatra, Kerala. I'd like to thank you for such a wonderful class. You've discussed so many questions and explained us very well. Thank you, ma'am, for your effort. Thank you, sir, for
Thank you.
organizing.
It's my pleasure.
Thank
Hello, sir.
Yes.
Sir,
Yeah, Dina.
ma'am, I'm
Yes.
Dina K from Government Victoria College, Palakkad. First of all, thank you, ma'am, for your wonderful class. Thank you for your lectures on the basics of metrics. It really helped us to revise and understand the concept very well. Thank you for spending your valuable time, ma'am.
No problem. That's my pleasure.
Thank you, Dina.
Hello, ma'am.
Hello.
Yes.
Hello, ma'am. I'm Gopika from Zamorian State College, Kerala. Am I audible?
Yes, yes, you are audible.
Okay, ma'am. Today's session is really nice. Matrix is one of my favorite topics, so I enjoyed the class really well. And thank you so much, ma'am, for spending your valuable time with us. And thank you, Vinod sir, for conducting this session. Thank you.
Thank you, Gopika.
Hello, ma'am.
Hello.
Yes.
Ma'am, my name is Abarna. I'm a graduate student, B.Sc graduate. Actually, this session was very helpful for me because it made me realize the concepts, the basic concepts of linear algebra. So, thank you for your spending your valuable time with us, and thank you so much, ma'am.
Thank you.
Thank you. Yeah, Nishita. Yes. Nishita, you are muted, I think. Please unmute yourself. Yes. Nishita, you're muted, I think. Please unmute yourself. Okay, others. Nishita may join. Yeah. Yes.
Verma from Samurian Sudharpan, Calicut, Kerala. And thank you for this informative section. And thank you for your effort. And thank you, sir, for conducting this. And thanks for everything. Could you please share the notes with us? Just-
Okay. I will send PDF to sir and he can forward to the group or.
Okay,
Thank you,
okay.
ma'am.
We can
Thank you.
share it. Yeah. Thank you, Nandana. Yes.
Hello,
Yes. Yeah. Yes.
I am Rosina. I am currently studying B.Sc Mathematics final year in Sri Krishnapuram VTB College. Today's session was very beautiful and very useful. Thank you, Vinod Kumar sir, for organizing a beautiful session for us. And thank you to Annu ma'am for conducting this beautiful session.
Okay. Thank you, Rasina.
Hello, ma'am.
Yes.
Gayatri. I'm Gayatri. I have studied in Miranda House College, Delhi. Thank you for taking a wonderful class. The notes that you have prepared was very nice, and you have discussed a lot of questions. That was really helpful to understand the concept more. Thank you, ma'am. Thank you, sir.
Thank you.
Thank you. Thank you, Gayatri. Others? Yes.
And thank you, ma'am. You explained each and every part of matrix theory so precisely, and so that we are able to memorize previous semester things we have learned. Thank you so much, and we are expecting you for more classes. Thank you.
Thank you, Akhila.
Thank you.
Yes, others?
Hello, ma'am.
Yes.
Hello.
I'm Malavika, third year B.Sc Math student of Jamur in Surarapan College, Kozhikode. Thank you, ma'am, for this.
Malavika, I think you are muted. Your voice is not audible.
Sir, now I'm audible.
Yeah, it's
Yes.
okay now.
I'm Malavika, third year B.Sc Math student of Jamur in Surarapan College, Kozhikode. Thank you, ma'am, for this wonderful session. It is really helpful for us. Thank you so much, ma'am, for your time and effort. I would also like to thank Vinod sir for conducting such a wonderful session for us. Thank you, ma'am and sir.
Thank you, Malavika. Others?
Ma'am, I'm Anamika from Samuel's Guelpan College, Kozhikode. Nice session, ma'am. You discussed very many more problems, and thank you, sir, for conducting this session. Thank you, sir. Thank you, ma'am.
Yes. Anu?
Yes, sir. Yes, sir.
Yeah.
Okay.
Yeah. Yeah. Her name is also Anu. That's why. Yes, Anu, you can talk. I think some net issue with her. Maybe. Any others?
Hello, ma'am.
Hello.
Yes.
My name is Unnimaya and I'm from St. Teresa's College, Ernakulam. Although we have learned all the basics of matrices from our plus two classes, we started from the very beginning and you explained all the basics as well as the jam level questions. So thank you, ma'am, for your valuable session.
Hi, ma'am. My name is Rasha, and I'm coming from Mr. Menon Memorial Government College. Thank you, ma'am, so much for today's class.
Thank you.
Thank you,
It was very
Rasha.
helpful, ma'am. Thank you so much. Looking forward to more classes from you.
Sure.
Mhm. Okay, any others?
Good
Yes,
afternoon, ma'am. Good
Kaushik.
afternoon, sir.
Yeah.
Kaushika Devi. I'm doing second year M.Sc in Krishnamma College, Coimbatore, Tamil Nadu. And this is my first session attending, and I really loved it. Thank you so much, ma'am and sir, for conducting. This is a huge initiative. I really loved the class. Thank you. Thank you so much.
Thank you, Kaushika.
Ma'am, for
Yes.
other than Hurston, is there any other book for algebra?
Sorry?
Ma'am, should I come again?
She's
Do you
asking for
suggest
some
any other book other than
suggestions.
Hurston? Books.
Annu, she's asking for some suggestions for studying the matrices and other algebra portions.
Okay. So I think that Hoffman and Kunz is a really nice book for linear algebra. If you want to make your concepts very strong, you can go for that book.
Yeah, Kaushika, you can follow the book by Hoffman and Kunz,
Hoffman and Kunz.
Linear Algebra. That's a nice book. And also there are some other books like Understanding Linear Algebra. I'm not remembering the author. And there is one book by Kumareshan, Linear Algebra, a Geometric Approach. That is very good for lots of exercises and also some geometric constructions. So you can go through that. I think the PDFs are available in Google. Yeah.
Okay. Yes, thank you.
Nishita, is your voice problem over now? She has started in the summer. Any others?
Hi, ma'am.
Yes.
My name is Zahra Rumaita, and I am from TMC College, Tirur. And thank you for this valuable session, and for nice preparation and presentation. And thank you, sir, for conducting this session. Thank you.
Thank you, Sarah. Any others? Otherwise, we may. Yeah, Nishita messaged me that her mic, she has some problem with her mic audio device. That's okay, no problem. So Anu, I hope that
Yes, sir.
today's session was really enjoyable one for you too, and
Yes,
it was really helping for the students that are very clear from their comments. So we expect you again in our platform to discuss all problems with the students in helping their preparations for JAM examination. And if you have anything specific to suggest them about regarding the preparations for JAM, if you have any tips, then you can share it now. That will be good for them.
So I think that make your concepts really strong. You can deal with any question of that subject with those concepts. Plus, because more of the questions are like you have to solve the questions, so practicing is the must. Is like really required for the exam.
Could you share something about your experiences in IIT Kanpur and their department there?
So that was really nice. There, I was not very good with like real part of mathematics. Real part. I was always fond of applied mathematics. But from there, I got to know how you approach any question. I was afraid of theorems. I didn't like proofs of the theorems. So, because I thought that you have to like memorize something to get to the proof. But when I went there, I saw how you approach a problem, how you see what is provided in the question, how you have to like they were not providing you with the solutions, they were just providing you a training like how you can go to the solution, how you can reach to the solution by yourself. That was a really good part.
Okay. Thank you, Anu. Anyway, your comments will be a motivation and an inspiration for our students. So once again, I would like to express my sincere thanks for being with us on behalf
Thank
of
you, sir,
our
for
Net
having me
Aspirants.
here.
Yeah, thank you. Thank you, everyone.